let's present the second problem, which is it's a problem called competency. So this one has a bit of an involved setup. So the setup is we have there are n cows in a row. There are n less than 10 to the 9 cows, and each cow has some competency, technically competency, but I'll just write competency, ranging, which is one integer from 1 to c, where c is up to 10 to the, at most 10 to the 4. C is some input parameter. And now we want to know, so these cows are going to stand in a row. So the cows are going to be like A1, A2, A3. It's going to be some sequence where each of the A's is just the competency of each cow. So like basically you have an array of each, where each value, so 1 to C. And this array needs to satisfy a few constraints. I'm going to use C instead of A because there's a different A in the problem statement. So, okay. So now there are a Q constraints that we must respect. There are Q less than equal to 100 constraints. And what do these constraints look like? Well, each constraint is going to be some pair A comma H. And what it says is that all of 1 through A, so the first A cows in the array, all of these cows, out of all these cows, H is the first cow to the right that is strictly greater. So to give an example, let's suppose that position A and position H are here and here, and we have some cows in between with like scores of like 1, 5, 2, and 3. And now this H means that the first position where something is strictly greater than anything in this prefix is right here. And so that means a possible array for which this works is like if we have a 6 right here that is strictly greater than anything in this prefix. And furthermore, everything in between needs to be smaller than, less than or equal to 5. So anything in between cannot be a closer maximum. The first maximum needs to be 6. So I'll put some values here, 2, 4, 1. So this will be an example of a valid array. But if, for example, this 1 was actually a 7, that would be invalid because 7 is closer. It is closer from the left to the left, and it's also greater than this entire prefix. So that would not be a valid sequence. And so now we are simply asked to count. Now we are asked to just count the total number of valid sequences. And since this number could be very large, we are asked to compute this modulo 10 to the 9 plus 7. All right, so that is the premise of the second problem. Now let's talk about how we can approach solving this. So if you took the silver version of this contest, you've actually already seen a variant of this problem because this problem, the same setup was given to you in the silver contest, except the difference that there, they didn't ask you to count it. They just asked you to construct the lexicographically smallest sequence that works. But some similar preliminary analysis can be done to understand like what sequences are valid. So let's first analyze like what conditions or what constraints need to hold for a valid sequence to exist. So I think the first observation, or this is not really an observation, but just the formulation that makes the problem like much cleaner to analyze is these A, comma H constraints can be viewed as intervals. Intervals from A plus 1 up to H. And so what this is saying is that if you look at it that way, then basically what this is saying is that everything in the prefix from 1 through A needs to be smaller than H, and also the maximum needs to be in at position of the entire interval from A to H needs to be at position H. So this needs to be the maximum of the interval, the strict maximum. So there are multiple maximums, then that is not allowed because the first maximum needs to be at position H. So that's another formulation of this, is looking at this in terms of intervals. Now, why is looking at intervals helpful? Well, now we can analyze some particular cases of intervals. So let's say we have some situation like one interval is here. Let's say we have a situation where one interval is here and the other interval is here. Is this possible? Well, let's suppose that the value here is well, let's say the value here was 1. And the value here was also 1. So this needs to be the first position that is strictly greater than anything inside this prefix. So this could be something that's 2, for example, and that would work. That would satisfy this interval. But now, that also means that the first position that is greater than or equal to this prefix, or sorry, that also means that the first position that is greater than this prefix is also this position right here, because this is 2, and not here, which is what we want. And so the only way this is satisfiable is if this is less than or equal to this. So this has to be 1. But if this is 1, then this is not the first position that is greater than this prefix for this interval. So we kind of arrive at a contradiction here. Like when two intervals are intersecting, or when one interval is nested within the other, it is never possible to have a satisfying sequence. So these types of cases are just simply not possible. So if we have some sort of nested case, we immediately know there are no sequences that exist. It's 0. What about intersecting intervals? Let's say the interval is intersecting. So one interval is here, another interval is here. Then let's try to satisfy this. So let's say this is a 1, and this has to be a 2. And now let's suppose that this is a well, what happens if we make this like a 2? If we make this a 2, then this would actually be the first position that is greater than this prefix. So that's not allowed. So this can't be a 2. This has to be like something smaller, like a 1. But if this is a 1, then the first position that is greater than this prefix is right here, and not all the way back here. So again, we have like a contradiction. If two intervals are nested, it is also just not possible. It's also just not possible to build something that works if we have two intervals that are intersecting. And so actually, the only cases where we can have a valid sequence are really simple. The only cases where we can have a valid sequence are when the intervals are completely disjoint. This is the only case where the answer was not 0, when there actually can exist a valid sequence. Because for this one, you can do something like this is 1, and this is 2, and this one also be 1, and this one we make it a 3, this one 1, make it a 4, right? And you get the idea, right? So like this is like the, or I mean, you can also have them like something like this is also allowed. So they don't necessarily. So when I say that disjoint also includes like it can be like right next to each other. So you can also have some situation like this. So that's 4, and then the 4 makes a 5 to make it satisfied. Yeah. So this is these types of cases where we have disjoint intervals. This is the only possible case where the answer is not 0. So from now on, we can just assume that we have just disjoint intervals. And when the intervals are disjoint, it is much easier to count the number of possible sequences. So I'm going to now have everyone consider the following dynamic programming approach. So we have these intervals that are disjoint. And let's say dynamic programming of I and J denotes that we are currently up to position I, and yeah, we are currently up to position I, and our prefix maximum is J. Now this would be O of n times c states if you just did like the exact position, but O of n times c is not allowed because n is way too large. N is up to 10 to the 9. So it needs to be O of q times c instead. O of q times c states. And the way we get to q is just like we only care about the relevant I positions. We only care about the ones that are endpoints of intervals. So specifically, we only care if we are either like here, the right endpoint of an interval, or here, like one before the left endpoint of an interval. Okay, now let's look at the transitions. So the transitions, what do they look like? Well, if it's going from like a right endpoint of an interval to here, then it really doesn't matter what's like in between. We can figure it out later. But let's suppose that we're going from like here to here. So we're going from the because these are disjoint intervals. So the only possibility is we're going from some left endpoint to some right endpoint, or from some right endpoint to another left endpoint. And so let's say we're in this case, we're going from the right one before the left endpoint of the interval to its right endpoint. And so that means, let's say we're going from dynamic programming of ij to the right endpoint, which is going to be dynamic programming of some new index k, and I'll say some j prime, some new prefix maximum. Well, what is the situation here? Well, the current prefix maximum is j. We have this interval. We need this to be strictly greater than j, and we need everything in between to be less than or equal to j, right? And so the transition is that to get to this new dynamic programming of k, j prime, which is k is really just like there's only a singular k, it's the next relevant position. We need to multiply this. This needs to like basically plus equal dynamic programming. We transition from ij, but multiply by the coefficient. Well, what is the coefficient? Basically we have any of these values in between can be anything less than equal to j. So there are j possibilities for each. The total number of them are like is like k minus I. Yeah, I think k minus I minus 1. And then k itself has to be set equal to j prime, which is greater than j. So our transition looks something like this. Now we just compute this naively. This is O of q times c squared, right? Because for each state, we iterate over all possible j prime for the next prefix maximum that we can possibly transition to. That's too slow because c is up to 10 to the q. For some reminders, q is up to 100, but c is up to 10 to the 4. 10 to the 4 squared is 10 to the 8. 10 to the 100 is 10 to the 10. That's too much. But we can speed this up from O of q c squared is just q times c with prefix sums. And the trick or the observation is that this multiplied factor, this j times j to the power k minus I minus 1, this is only dependent on the state we transition from. It has nothing to do with j prime. So instead, we just compute prefix sums on dp of ij multiplied by j to the power k minus I minus 1 for the previous layer, and then just use prefix sums to compute all of the new dp states really efficiently, just by adding all the previous j less than equal to j prime with their appropriate factors multiplied on. And so this speeds it up just from O of q c squared to just O of q times c. It might be q times c times the extra log factor or something, because when you pre-compute this, you need to use binary exponentiation to compute j to the power of k minus I minus 1 efficiently, where this exponent can be up to n. So you might need an extra log factor to compute the modular inverse quickly, or not modular inverse, but to compute the j to the power k minus I minus 1 efficiently. But that's still fine. Yeah. And so now we finally have a fast enough solution. So to recap, the keys to solving this problem was observing that the intervals have to be disjoint, and then after that, writing some sort of dynamic programming to compute this number of sequences where the intervals are disjoint, and then using prefix sums to speed up the dynamic programming transition. All right, so are there any questions on this problem? Okay. I got one more problem then. Let's quickly cover that.